Let me share screen.
Sure. This is a 40-minute Zoom, so we'll just do, I mean, you can just do the, I mean, okay, so it's the 10 questions on here?
There's like 10, 10, 10, probably something like that.
Okay, yeah, that should be enough, honestly. Okay.
Okay, so this one, probably need the periodic table, right? No, never mind. So atoms of an element X have the electronic configurations shown above. So the compound most likely formed with magnesium is, okay, so X has this electronic configuration. So if we go to the periodic table, it ends in 3p3. So 3p3 would be here, phosphorus. That's the question. So it would probably be what? So Mg is 2 plus.
Mm-hmm.
Yeah, and then phosphorus would be
3 minus, I think.
3 minus, yeah. Okay, 3 minus. And so if you want to have a compound with 2 plus and 3 minus, you would need 3 of these and 2 of these, because then you get 6, positive 6 and negative 6, which balances each other out. So Mg3 and X2, like we said, would work. So should I answer? Yes. Okay. Oh,
you have to hide answer, Neha.
Yeah, I forgot.
Okay. It's okay, I do the same thing.
Which atom below contains exactly 2 unpaired electrons? So 2 unpaired electrons would be, well, you have to look at the electronic configuration and just like figure it out. So we saw that the answer was Ni, so I'm not going to go through the rest of these. So why would Ni have 2 unpaired electrons? So if you go to Ni, which is where?
What is Ni? I don't even know what Ni is.
Oh, it's here. It's nickel. Okay.
Nickel. Okay.
So nickel would be would end in 3d8. So with 3d8, there's 5 boxes to fill. So 1, 2, 3, 4, 5, and then 6, 7, 8. There's 2 left over. So that's why it's 2 unpaired electrons. Okay. Which atom contains only 1 electron in the highest occupied energy sublevel? Okay, so this one would probably be like an S1 atom. So which one would be an S1? Mg, As, Sc, Br. That's none of these, right?
So it's asking for the highest occupied energy sublevel. Mg,
yeah,
Sc,
As,
Br. Only 1 electron. The highest.
Wait, is sublevel like SPDF or the numbers?
I would think just valence electron, right? So it should only have 1 valence electron, essentially, right?
Is that what it's asking?
The highest occupied energy sublevel is the outermost shell, right?
Yeah, so it's not Mg.
It's not Mg.
Mg has 2. And then As, Sc. So As is arsenic. No, it's not that.
That wouldn't be
and
make
then
sense.
It might be Sc. And then where's
it
Br?
It might be Sc and
Br. It's also not Br. So yes, it's Sc.
Because I guess it would be Sc. Yeah.
It's only 1 in 3D, so it's 3D1. So that would be Sc. Yeah. Okay.
So I think so. SD actually isn't. It doesn't. So in that case, it wouldn't be valence electrons because
yeah,
valence electrons are only S and P, right?
Mm-hmm. Okay. The table shows the first ionization energies. Okay.
That looks like an actual AP question. The AP font.
Oh, is it? Okay. Yeah. So, which explains the deviation of oxygen from the trend?
They put these on FRQs as well a lot. These types of questions. So these are good questions.
I'm honestly not sure about this one.
Can we go back to the periodic table? So it's asking about first ionic energy, right? Or ionization energy.
Yeah.
And ionization energy means the energy required to remove an electron, or yes. So ionization energy will
maybe it's because it would be half full, right? Is that why? One from oxygen, it would be half full.
Yes, because it reaches a position of stability when it's half full. Exactly.
So, which one would it be?
The atomic radius. No, the atomic radius of oxygen. No, there's repulsion between paired electrons. There's attraction between paired electrons. I think it would be repulsion. Yeah.
Okay.
Why? Because think about it, right? You have 1, 2, 3, and then another one. So it's so close to reaching a stable state that it's a little bit unstable. So the two electrons that are paired want to repel each other. It wants to get away.
Okay. The ionization energies are listed in the table on the right. So this one has a really big jump from third to fourth. Mm-hmm. So you want to see how would that trend take place. So I think it's harder for me to explain it. I just have to like look at it. So let me figure out how to explain it. So
what I do is I look at the jumps on the periodic table. I think of it in terms of jumps.
If there's a big jump from first to second, then that means that the element is in the first column. So since there's a big jump from third to fourth, it's in the third column. So which one of these is in the third column? B, E, C, B, F. None of them. Okay. Oh wait, we can also look here. Sorry. Yes. Okay, yeah. So it's B, because in this row, this is the third column technically. So yeah.
Oh wait, so it's talking about but it's between the third and the fourth, right? Mm-hmm. So first ionization energy.
I think it should be there. B. I'm pretty sure. Yeah.
Okay. Yeah. Okay. Yeah, your reasoning was fine. Like you said, because if the first ionization energy is high, that means it's in the first column, and yeah, your logic was perfectly fine.
Okay. So for element X represented above, which of the following is the most likely explanation for the large difference between the second and third ionization energies? Okay, like as we said before, there's a jump because it goes to the next energy level down. So what would that be?
The electron removed during the third ionization is on average much closer to the nucleus than the first two electrons removed were. I think it's that one.
Yeah, it's that one. Yeah, it should be.
A lot of the time, I don't know, this is a trend I noticed. Sometimes the longer, more detailed answers are correct.
Yeah, that's true. Okay. Which of the following is the electron configuration of Ag+? Okay, this should be pretty simple. Electron configurations are pretty easy. So Ag+ means that there's one less electron from Ag. So where Ag is here, so that would be, normally that would be 4d9. And so if it's Ag+, it should be end in 48. So let's see, that should be, or there's that trend that happens where,
wouldn't it be 5s248 then?
Wait, what is the trend
you're
again?
saying that it'll be the trend where it switches, right? So it could very well be the krypton. Huh?
Would that
Sorry,
happen?
Can you go back to the periodic table 1 second? So you're saying Ag plus, the thing is, Ag itself doesn't do that, does it? Ag itself, what would Ag itself be? It would be 5s2 4d9, right? Mm-hmm. 49. 5s2 49. So since it's 5s2 49, when you remove the electron, it becomes 5d8. I don't think it would change orbitals. I don't think it would change orbitals.
It should be 48. Oh wait, it's right here. So. I didn't even see it.
45s to 48.
I thought they didn't give us this choice. Okay, I didn't even see that.
Now, if it was asking it for, it is 4010. So okay.
So how do they do that though?
See, I don't know. That's something I don't think I ever went into last year. Was how the rules on that.
Can they just take 2 from 5s2 and just put them in 4d?
I understand why they're doing that because it's, I guess, more stable, but
But can you just
How
get
do you
rid of
know that?
5s2 altogether?
Let me search it up. Or how about you search it up as well, and then we can, because it's better to clear this up right now than to have questions about it. When do electrons jump down for stability?
This is strange.
4D.
Okay, so here it says, oh.
Oh, that's the electron configuration for silver itself?
Yeah, I forgot. Don't you take it out of the highest energy level? So you take it out of 5s anyway. I forgot.
Oh, because it had 4010 to begin with?
It had 49, but since when it was Ag plus, you're supposed to take that extra electron out from 5s, not 40, which was my mistake.
But what they're saying here is silver itself, not the ion. Silver itself has 4010 5s1. So that means
yeah, that's the stability thing.
That's a stability thing. Okay, so rather than going from 5s2 40, what was it? 5s2 49, it took one from the S and put it in the D to get that 4D stable first. Is that what it's saying?
And then it took out another one from the S.
The S. I got it.
Okay.
Okay.
Yeah, I forgot. Sorry, my bad. Let me.
It's okay.
An electron, an atom in an excited state. So first, let's rule out the ground state ones. So this looks to be ground state, I think. And then
how do you have 4s3?
Oh wait, oh never mind. That's weird. Okay.
Yeah.
But this is ground state, I think. And then this is not ground state. This isn't even a thing, actually. 2d10 is not a thing.
Yeah.
And then this is not ground state. I think this is excited state. I'm pretty sure.
3s1, 3p6. That looks like it's excited state. Yeah.
Yeah. Okay.
Yeah. Because the S isn't full, but P is full, right?
Yeah. Excited state just means that one electron from a previous, or like however many electrons from a previous sublevel go up to the next sublevel. So we ruled out this. We ruled out this one because it's ground state, it's just normal. And then this one we ruled out because 2D is not even a thing. And then this one we ruled out because you can't have 4s3. It's only, you can't put more electrons in there. You can only like have one less like this. Okay, so photoelectron spectra. Okay, so this one looks like there's about 2 here and then 2 here, right? So, or no, this is two different two
isoelectronic species. So they're sorry. Okay.
Ca2 plus and Ar. So Ar is here, Ca2 plus is here. Okay, so which of the following correctly identifies the species associated with peak X? Okay. Okay, so Ca does have more more protons because it's, it just has more protons.
Yep.
And it has 2 less electrons. So the protons are going to attract the electrons more more strongly than Ar would because it has more protons. So there's more attraction between them.
So binding energy would be higher, right? For Ca2 plus?
I think it's this one then. Yeah. Okay.
Yes. Yep. This is another common one that they use for FRQs, that with photoelectric. I don't even remember what they're called. Spectra, photospectra. I don't know.
So this is non-flammable. So based on its properties. So this is nonpolar. So what else could probably be used as a fire-resistant chemical?
Probably CBr. What is Br? Is Br?
Why
is Br in group 1 or? Yeah, it might be CH4.
I think
is
that
bromine?
Right.
Where is bromine on the periodic table?
It's the one. It's this one.
No, that's boron.
Oh, no, wait, not.
No,
sorry,
I think it's CBr4.
CBr4. Okay. Why is it not?
Yeah, I think it's CBr4.
Like what?
Wait, what was the other one?
What makes it not CH4?
The original
though?
was CCl4, right? Because when you're doing these types of problems, what I do at least
Oh,
is
I see.
I
Yeah,
just
yeah.
look at the
Cl is
first one and I
closer.
see or not even closer. What matters is the groups, the period, the
Yeah,
columns.
sorry. Yeah.
Columns are what matters. And
Mhm.
since C obviously isn't changing, the Cl, the best substitution would be either F or Br.
Yeah.
H is you get methane, and methane
Yeah, so essentially,
is actually highly flammable.
oh yeah, yeah. Okay, so you want something as similar to the original as possible, and so CBr4, Br is very close to Cl, and it's in the same column, so it should have the same properties. So yeah, okay. And this is it for this one. We can move on to this one.
Cool.
Okay, which of the following are covalent? So there's more than one, apparently. Covalent should be definitely this one, and then it's not NaI because Na is in a separate place. Like it's going to be an ionic bond. Na is over here and I is over here. Okay, so sorry. Let me X this out. No, actually I want to save that. I'll put in the chat.
Yeah.
For okay.
Oh, okay.
So I think it's going to be this
pin it
one.
if you want.
Oh, that's fine. And then this isn't even a compound. It's just an element.
Yeah.
An atom. And then this, I think it should be this one too, NH4 plus.
Yes, but that's a polyatomic ion, right? Right? That's the ammonium ion, I believe. I've forgotten. I'm surprised I remember as much as I do, but
I don't remember.
I think that's a polyatomic ion.
I just thought because NH are both, I think it should be.
Yeah, I see what you're saying. They're both gases.
I'm sorry.
But non-metals. They're both non-metals.
Let's see.
NaI
I'm not sure.
wouldn't work.
I'm not sure. No, NaI was the one we said was ionic.
F2 is for sure covalent.
Okay, so then it should be these three, I think. Yeah. Okay.
Okay. So they're counting polyatomic ions?
I guess they are. I'm not sure if this would actually count though.
So no, I guess they're right. I mean, technically they are covalently bonded in a way. Because remember, it's more of a spectrum, right? It's not like in reality, it's not like this is ionic, this is covalent.
Yeah.
It's more of a spectrum.
Okay, let's move on. Which of the following bonds will be the most polar? Okay, I actually looked at this one before and I didn't understand the answer. So basically, I thought it would be BF because I just did 4 minus 2, which is 2, and that's the highest. Like,
are these electronegativities?
Yeah, it's the difference in electronegativity. I don't know if you can read it, so I'll say it out loud. So CH would be 2.5 and 2.1, which is pretty small. So I don't think it's that one. And then OO
same thing. So obviously, yeah.
And then SiO would be 1.8 and 3.5, which would be a difference of 1.7. So I thought 1.7 is less than 2 for BF. There's a difference of 2. So I thought it would be BF. Yep. But it says it's SiO.
It's SiO.
I'm not sure why, honestly. But I'm pretty sure you just have to look at electronegativity and see the difference to see which is the most polar.
I think it would be BF.
Maybe there's a mistake. I'm not sure.
Maybe if they give you a chart of electronegativities, then obviously the one that would be most different is BF inherently. No, it can't be because no, that wouldn't make sense. I think BF is the most polar, especially because you have F, which is one of the most electronegative.
Yeah, I would think so. I think there might be a mistake in this one. You have to look at the difference in electronegativity to figure out which would be the most polar. Okay. So which explains why copper conducts electricity. So what we learned first about metallic bonding is obviously delocalized electrons. So probably be this one. Yeah.
C of delocalized.
So this is another checkboxes one. So atoms are most likely to form a bond when. So we know that this is true. We know that valence electrons are attracted to the nucleus of another atom that forms a bond. And I think it's the lowest potential energy possible because that would mean that there's actually I can't explain this because I just learned it, so I'm not that familiar with it. Can you explain it?
Atoms, I don't think I know, but let me try and reason through it. So They're most likely to form a bond when they're at their lowest potential energy possible. Highest potential energy possible means that they're at a transition state, right? Wouldn't
not
it
sure.
be highest potential energy then?
It's well.
Is it lowest
We
potential?
learned it was in like this FRQ that we had to do that like when it's at the lowest potential energy, it's most likely to like form a bond, and I think it's because I couldn't explain it. I just knew that that was what it was. Let me see why. So.
Because it lowest potential, highest potential energy means it's what does it mean for are we talking about the electrons?
Yeah, I think so, right? No, it just means the atom. Okay. Okay, so potential energy decreases as the bond.
Oh, that's right. That's right. That's right. This was added to the curriculum pretty recently. Search up bond length and bond energy video, or sorry, graph. This was an FRQ on the AP exam last year, and I think I remember I had learned that, like, I saw it on the CED, the course exam description at the very end.
I'm pretty sure that like
this graph,
when the bond length is smaller, there's a higher energy, right?
Yes, there you go. So stuff like that, whenever your potential energy is minimized, is when they're more likely to. That's when they're more likely to bond. Do you see that chart? That's yeah.
Yeah, that's what we learned. Like, we learned it for this unit, so I'm not familiar with that with it. But like, I just know that when it's low potential energy, it's like.
And they don't talk about this in most books, which is why. Okay. And what was the other one again? The other answer choice?
It was when they're close enough for valence electrons to be attracted.
Of course.
That's obvious, I'm pretty sure.
So this is directly referencing that chart, I guess you could say, right? That table.
Yeah, I think it is. It's really it also might be related to like Coulombic attraction, maybe.
Coulombic attraction, yes. Yeah, for sure.
Okay.
Because it's and Coulombic's I don't know if people have noticed this, but Coulomb's law is pretty much I mean, it's very similar looking to the law of gravitation.
Yeah, I noticed that too. Yeah.
Yes, and that's not a coincidence. It was very it was noticed, and that's something that that's a way that people actually remember the two of them.
Okay, so this one should be pretty easy. Cations and anions. So obviously ionic. Okay, there.
Yep.
Okay, highest melting and boiling points. So which of these would have the strongest, basically the strongest bonds? So it's not covalent, and I don't think it's metallic. So I think it would be ionic again.
Yep.
Okay.
Because ionic bonds, you have the lattice energy, which is much stronger.
Yeah. Okay, so name this technique. Heating a substance, allowing it to cool, and then weighing it. Okay, we didn't learn this, but I think we might be able to just.
Steps. Let's see.
Okay.
It looks like a weighing boat analysis.
Is it? What is it?
Hold on. So you heat it. What are we doing? Let's see. We're heating the substance, which means we're getting rid of the water, allowing it to cool in a desiccator.
I think it might be heating to
repeating the
mass.
steps.
Because if it's until no further changes in mass.
Yes, it's heating to constant mass. Yeah.
We didn't learn this anyway, but.
So this is I don't think you need to know the name of this technique per se, but this is something that they do on the FRQs when what they do is they'll have some sort of stoichiometry question attached with this. They'll say, okay, we've heated this over and over again, and then the last few times this is what the final mass is, and then they'll ask you, okay, how much of it was water, and then you'll do some stoichiometry with that. How much of it was the actual unhydrated? I don't remember what the terminology is anymore, but yeah.
Okay, yeah. So here we have Coulombic forces. So Coulombic forces would mean, like higher Coulombic forces would mean higher attraction. It's like, more force. So if there's more attraction, then it would be hard to separate the different molecules. So, oh wait, we're almost out of time. Let me just get through this quiz. Okay, so I think it should be this one.
Yep.
Higher Coulombic forces will lead to higher BP and MP. Okay. So this one, I think it's what we were looking at before. So it's this is the potential energy, I think, maybe.
Yeah.
So the largest atomic radius, to be honest, again, I'm not familiar
So
with this.
I would
Can
go
you
back to
explain it?
the graph, like the one that you search on Google,
Mhm.
and then go to which one? The covalent bonding one, the one to the left of that. No, the one right below the one you're clicking right now. Yes, that one. That's the one I used to reference a lot. So it's in its most stable state, meaning it's bonded when the potential energy is lowest. Meaning the more that valley, the more that local minimum is shifted to the right, the more I mean, sorry, hold on. The more
I think it should be the red
I think it would be
one.
the red one too.
Yeah, okay.
Yes.
So yeah, okay.
Using that logic that we said earlier, the more that it's
So NH3, N would need an additional lone pair. So I think it should be this one.
Yes.
Okay.
And NH3 is one you should probably try to memorize. I mean, not intentionally, but from practice, memorize, because that's something that comes up in organic chemistry a lot.
Okay, so total valence electrons in bonding. So just count up all of them. So this should be 1, 2, and then plus 4, so 6, and then plus 6 is 12. But then these 4 are not participated in bonding because they're, they're not. So it should be 8, I think. 12 minus 4 is 8. Let's see. Yeah. So BF3 is that one that we needed to memorize, which is an exception to the lone pair rule. So it would not have a lone pair. This one, it's just fine being like this, and it would not need a double bond either. So I think it's A. So yeah, you just have to memorize
Remember
that.
the one with the electronegativity differences? Was
Yeah.
that B and F?
It's just BF, yeah.
Maybe that was the reason why, because BF is the one that does the weird thing with. But if it was just BF though, I don't know.
It wasn't BF3. I don't know.
Yeah,
I'm
it
not
wasn't
sure about that
BF3.
one. That one was just a weird question.
Yeah, that one was
Yeah,
weird.
I think it should be. I mean, obviously it is. It is BF3 because that's just how it is because of some reason that I know vaguely, but I can't explain it, and you can search it up if you want to know. So this is incorrect. It looks incorrect, pretty glaringly. There's double bonds for each of these, and so this is a checkbox one. So it says it should be this one. I'm pretty sure there should only be single bonds, and then check boxes. So another one of these. It doesn't need a triple bond. I don't know what this is even saying, honestly. Oh no, I do, I guess. Yeah, I think it's saying that there's only 6, but there's still 8. Like it still has 8. So
Yeah.
I think it should be this one. There should be more lone pair atoms because if you change it to single bonds, yeah. If you change it from single bonds, I mean from double bonds to single bonds, then it should give it another lone pair. Okay, so yeah, these
there's
two.
another. Yeah. Okay.
Okay, the shortest bond length. So since the longest was
the atomic radius is the distance from the x-axis, or I guess you could say the r-axis, to the minimum value of energy. So the purple would be
Purple, okay.
Would be the one with the shortest bond length. Yep.
Okay. So a 3:2 ratio of mg to n. So again, you just have to look at the column for this one because it would have the same number of valence electrons. So what would bond with mg in the same ratio? So it would be in the same column as n. So there's phosphorus. So yeah, phosphorus is here. So yeah, okay. And then I think we're almost out of time, but we can just look at as many as we can do for this one. There's 26. We're not gonna finish, but it's fine.
Yeah, that's fine.
So which experiences dipole? So this is obviously covalent. So I don't think it would have that.
Nonpolar, I think you mean.
Oh, sorry.
Yeah, it is covalent, but it's nonpolar. Yeah.
Sorry, I meant nonpolar. Yeah.
Yeah.
Okay. And then this would also be nonpolar. And then I think this one would be 2. So I think it would be this one.
Yes.
Oh. Wait, I have an account. I was here. Wait, are you
Usually
if
it has
account?
carbon, huh?
Sure.
You were logged into the other ones. I see. Okay, go ahead. Yeah. Usually if it has carbon, and yeah, usually if it has carbon and 4 elements, usually it'll be nonpolar.
Okay, yeah, SO2. Because it's not going to be it's going to be polar, because it's not symmetrical. You can just look at the structure. Okay, and then a sample of a solid substance does not conduct electricity in either solid or liquid. So it is soluble in water. That would probably be something that's polar. So I think it would be dipole-dipole. Yeah. Because water is very polar itself,
Yes.
and like dissolves like, so we know that it would probably dissolve a polar substance. Okay, based on Coulomb's law and the data in the table above, which of the following would have the weakest interactions with an adjacent water molecule? I don't really know what to do about this one.
Based on Coulomb's law and the data, okay, which of the following would have the weakest interactions with an adjacent water molecule?
So you want a small radius, so maybe it would be Ba2 plus because it has a large radius, because that would have weak interactions, I think. Yeah, because with Coulomb's law, the smaller the radius, the stronger the forces.
So then the larger the radius, the less the interaction. Yep.
Which of the following molecules is least soluble in water? So a non-polar molecule would be the least soluble. It looks like this one would be non-polar. It seems symmetrical just from looking at it. Yeah.
Yeah, whenever you have a hydroxyl, and if you take biology, you would know that whenever you have the hydroxyl group, it increases the polar quality of it.
So at room temperature, it's a gas. So which is a characteristic of chlorine with the correct explanation? At room temperature, it's a gas. So that means it has a very low boiling point. Okay. I mean, this is the only one that talks about boiling point, but I'm still not sure about this
The
one.
last one is correct too, right?
This one?
The very last one. The chlorine is soluble in water because chlorine is polar.
Like chlorine itself is polar?
No. I think it's talking about chlorine gas. Usually, when it refers to chlorine, it's referring to chlorine gas. But it's not.
Okay,
no,
I'm not
sorry,
sure.
it's not polar. It's non-polar, so it would be 8.
Oh yeah, I think it. I was just thinking because it mentioned room temperature and gas.
Okay,
I thought it would be something about boiling point. So I thought yes, it has a low boiling point. Okay. Oh, I have a question. When it ends the meeting, if it like ends it without me ending it, will it still save the?
Yeah, it'll still save the recording. Yeah.
Okay. Which liquid has a higher vapor pressure at 25 degrees Celsius and why? Okay, vapor pressure. I think what a lower vapor pressure means.
Higher vapor pressure means that it was able to boil more easily, right?
Okay.
It was able to boil more easily means a lower boiling point, I would think. So CHBr3 would be the answer, and it's because it has weaker intermolecular forces than CBr4, I would say.
Okay.
Oh wait, that's wrong. Yeah. I'm so sorry. It's the other way around because CBr4 is the non-polar one, right?
Wait, I thought you said that higher vapor pressure is for higher boiling point.
Okay, hold on. Let me think about this for a second. Higher vapor pressure means we were able to boil more easily, which is why we have more pressure from the vapor. And we were able to boil more easily. There was a rule for this that I forgot, but I'm pretty sure non-polar things